Welcome back. If you are watching me for the first time, hey, I'm Sandeep Sharma. We just spent 11 videos breaking down the transformer architecture and LLMs. We learned something really beautiful. That is, these AI marvels are really good at guessing the next word. That is the magic trick. The world changing idea is literally what word comes next. Now, here is the question to you. And really think about this that if the idea is that simple, then why did 6 years? Why did it take 6 years from the 2017 Transformer paper to ChatGPT? Why did the brilliant researchers with billions of dollars at big companies, Google, OpenAI, struggles for years? Today, I'm taking you behind the scenes. We are uncovering the secret war that almost killed AI before it began. So, it is 2018. The transformer is the talk of the town, and researchers everywhere was excited. The math was beautiful, the code works, and everyone is thinking that that's it. This is the golden ticket. So they do what engineers do. They build bigger, more layers, more parameters, and and more power. Then silence. For months, nothing works. Models that should be getting smarter are getting dumber. They are not learning at all, or worse, they are exploding. Think about this. There was a ghost in the machine, a silent killer, and nobody could figure out that why these beautiful transformers would not just scale. Let me show you the ghost. It is called the vanishing gradient problem. You must have heard about this term vanishing gradient problem if you have some kind of understanding of deep learning networks, deep neural networks. So imagine you are teaching a 24 layer transformer model. You showed it a sentence and it makes a guess, and then you say, wrong, try again. That try again is the signal. This signal has to travel back from the last layer all the way back to the first layer. First layer. It has to travel through all 24 layers of decoder transformer. Okay. Now, if each layer slightly weakens the signal, let's say multiply by zero point 0.9, then zero point 0.9 multiply by zero point 0.9 multiply by zero point 0.9 to 24 times, then the output is basically 8% of the original signal. So the initial layers are failed to learn. The learning was happened in the earlier layers from the top, but the bottom layers are did not learn. So that's why this vanishing gradient problem arises. But oppositely also happen. Sometimes each layer amplify the signal. Then in this case, let's multiply by 1.1. Each layer amplify the signal, and we are multiplying 1.1 to each time 24 times, and it will become like 10% stronger. So in this case, the model panics, weights go crazy, and the training collapse. So this is called the exploding gradient problem. So we are stuck at this point. Researchers stuck at this point. Whenever they try to make deeper models, then this problem arises. Too weak to learn or too strong, everything collapses. So welcome to 2018. This is the first problem faced by researchers. Let me take you to the one note so that I can explain you simply using simple neural network. So I take this simple neural network, and this is our input layer. This is our input layer, and these two are hidden layer H1, H2. This is our output layer, and these neurons are present in this architecture, and in each neuron we all know what is happening. We are multiplying our input to the weights and adding a bias, applying activation function. This is happening inside, this operation is happening inside each neuron. Let me write it here: x multiplied by weight plus bias, and we are applying activation function. This operation we are doing in each neuron. Okay, so this W1 is basically W1, 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 and this is W2, W2, W2. So each weight is going through this second layer, that is called first hidden layer, and then pass it to the. So basically there are three main operations are we do in neural networks. First, we pass input, and it processes through each neuron, each layer, and we get our prediction. So this pass is basically forward pass. So first we do forward pass. So this is forward pass. Then we compute loss of this prediction. Then we compute loss, and that is also called, when we do the derivative of loss, that is called gradient. The signal that we talked about earlier, the signal derivative of loss. And after computing the gradient, we do the backward pass. We do the backward pass. Backward pass. In each deep learning neural network, in each neural network, training of neural network, these two operations, these two pass happen to train this neural network. One is forward pass and the other is backward pass. Okay, now let me tell you that we have our input x1, x2, we have target y, we have also learning rate. Learning rate basically decides how fast decide the speed of the training of neural network, that how fast we want to converge or how slow we want to go. Okay, so I write it that W1 is basically 3 into 2 matrix. 3 into 2 matrix, because in the input layer we have two neurons, and in the first hidden layer we have three. So 3 into 2 is our first weight matrix. Then similarly bias also, there are three biases present in each neuron. So like this W2, we have W2, B2, W3 and B3. These are our weights and biases. So in forward pass or forward propagation, we do the simple maths that first we multiply with weights and add a bias and apply a activation function. Activation function is basically we use to introduce non-linearity in our neural network, so that our network can capture complex patterns from the input data. Okay, so the formula of ReLU is basically max of 0x. This is the formula, and the graph is basically this. This is the graph. So whenever any negative value, the result of the ReLU, the output of ReLU is basically 0. So this simple operation we do in at each step, at each layer. Then our in layer 2 similarly we do the this operation, and in output layer again we do this, and in the output neuron we have the linear activation function, that is, and y cap is our prediction. Okay, then I said we compute loss. Loss is basically tells us that how wrong our model is. That we show a sentence to our model, and then it makes a guess, and we said it that wrong. Why wrong? Because we see the loss. If the loss is high, then the guess is wrong, and it will travel uh, using back propagation and updates weights and biases. So the whole thing is to update weights and biases in such a way that then in next pass the model will return a good prediction. So what is happening inside back propagation? That let me tell you. I told you in my previous videos that weight update formula W new is equal to W old minus learning rate times derivative of loss derivative of W old. Okay, so this is the gradient that we are talking about, and in this formula, so after forward pass, we reach at this point. Now we have to travel back and we have to update this W3. So we move like this. Okay. So first we need to update this W3 and B3. The same happening with the biases also, that B new is equal to B old minus learning rate times B old. Okay. The same we will do for the bias update also. But for now, I'm only showing you how weights are updates. Okay. So first we have this loss. We'll do first derivative. And how we backpropagate? We use chain formula. We do derivatives, and using the chain formula, we will update these weights. So this loss is depends on this y cap. So we can easily y cap minus y. This will be the output of this derivative. Now, now pay attention at this point, and this is little confusing, but if you watch the video carefully, then I make sure you will not confuse. Now let's see what is y cap. So we will go, y cap is basically Z3. Y cap is Z3 and Z3 is basically this. So we need to reach at this point. We want to get derivative of loss with respect to this W3. So we will use these terms. Y is equal to Z3. Then we can easily find derivative of y cap, derivative of Z3. Okay, this will be 1. Okay, and Z3 is basically, what is Z3? W3A3, W3A2 plus B3. W3A2 plus B3. Now we can find W3. So this is A2. Don't worry about the values. We just wanted to know the derivatives. That how we will get this term, derivative of DL D3. Okay. So basically, in this neural network, we need three derivatives. Okay. Let me write first the derivatives that we need. We need three derivatives. Derivative of loss divided by W3. Derivative of loss dl dw2 and derivative of loss dw1. We need these three derivatives so that we can use these three into this formula and gets the new value of our weights. Okay, so for first this term we can write it like this: derivative of y cap divided by derivative of Z3 and Z3 divided by W3. So eventually this will get cancel out, this will get cancel out, and this is exactly the same term we need. So we have the value of this derivative, we have the value of this derivative, and same for this derivative. So in this way we can find this derivative, and this is the chain rule. Now similarly we want derivative of L, derivative of W2. Okay, so so we can write it like this: derivative of y cap is Z3. So we can write Z3. Now W2 is where? Where is W2? W2 is inside this term. So this time we will do derivative of A2. This will give us A2. Okay. And what is A2? What is A2? A2 is value of Z2. A2 is a value of Z2. And what is Z2? A1 W2 plus B2. So we can write it Z3 derivative of A2, derivative of A2, Z2, and Z2 divided by W2. So this will be the result of the second derivative. So you can see now that how many derivatives multiplication we have to perform. Similarly, if we want to calculate the same for W1, so again we will do this like this: Z3, Z3, A2, A2, Z2. Now Z2 is basically A1 because W1 is present inside this term. Then we will do similarly A1. So A1 is basically a value of Z1, and Z1 is equal to W1 X1 plus B. So here A1, Z1 and Z1 W1. So, so you can see that this time we have 3, 3, 7. So 7 multiplications at this time. So we are talking about vanishing gradient problem and exploding gradient problem. So just look at it. Here we have only two hidden layers. We have only two layers. But what if we have 24 layers? Then if we have 24 layers, then how many derivatives we have to, how many derivative multiplication, how many multiplication we have to perform? So let's suppose if, again I'm taking you the same example, that if each layer slightly weakens our signal, our low signal, that zero point 0.9 multiplied by zero point 0.9 multiplied by zero point 0.9, so 24 times. So this will become very small number, very small number. It means too weak to learn. But if each layer amplify the signal, then 1.1 multiplied by 1.1 to 24 times, then it will be a bigger number, 8.9 something. So this time 8 times stronger than the original signal. So when weakens the signal, there will be vanishing gradient problem, and when each layer amplify the signal, and that makes it more stronger, when we do back propagate, then there will be exploding gradient problem. So this problem arises when researchers try to scale the transformer architecture. When they increase the number of layers, they suffer from the vanishing and exploding gradient problem. Now imagine, now imagine you are a researcher at Google, OpenAI, big company, and it is 3 a.m. You are at your 50th experiment. Every time you add more than 12 layers in transformer architecture, then you fail. You check your code, the loss curve basically, sometimes it looks like a roller coaster, sometimes it is a flat line, sometimes it shoots to infinity. You check your code, you check the paper, you check the math, everything is correct, but these beautiful transformers just doesn't work. Now here is what makes this more frustrating. The transformer paper showed it working. The the attention was brilliant, the architecture made sense. But when people try to increase the layers, the model that should be understand language, it was not. It it was hitting the invisible wall of vanishing gradient problem or exploding gradient problem. So this was the dirty secret of AI research that was happening in 2018, and for almost a year we had the blueprint of intelligence, but we could not be able to build deeper models. Now you might think that okay, can't we use 12 layer instead of 24 layers? Problem solved. But here is a twist. The depth is where the magic happens. Let's suppose you have 24 layer model, and the first layer understand the letters, the fifth layer understand the words, the 10th layer understand the grammar, the 20th layer understand the meaning, and the 30th layer connects the ideas. So deeper models are better, and everyone knows, but they were not able to train it. Why? Because of vanishing and exploding gradient problem. Now let me tell you the interesting part of this story, that vanishing gradient problem is not only one killer. There are three killers. It was three killers hiding behind each other. Let me tell you these three killers. The first one is optimizer trap. The original paper used Adam optimizer. If you don't know about optimizers, just in our in next videos we will discuss about optimizer. But for now, original paper used Adam optimizer, and there was a hidden bug that how this optimizer handles weight decay. That makes training unstable. So this is the first problem, first killer. The second killer is dying neuron problem, dying neuron trap. In transformer paper, we have used ReLU activation function. It is simple and efficient. The formula we know, max of 0 and x. But using this formula, the problem came. And what is the problem? The problem is dying ReLU problem. See, when the gradient value is negative, it will return 0. So due to this, the neuron turned off permanently. There will be no learning uh, due to this problem. So this is the second problem. And the third problem is architectural trap. There was a flow in transformer architecture. It used normalization, but the normalization is was in wrong place. So this is the third problem. So due to these three problems, researchers was facing issue in building deeper models. Now, lastly, let me tell you the very interesting part of the story that these three problems was not solved by any one genius. These three problems fixes by three different teams from three different places, solving three different pieces of puzzles. University of Tokyo fixed the optimizer problem. Google Brain solved the activation problem, and the open research community solved the third problem, architectural problem. So when these three fixes came together, something magical happened. We were able to make deeper models, able to train deeper models, 24 layer work, 48 layer work, and even 96 layer work. The ghost was gone, the invisible wall vanished, and for the first time we could build deep. This was the moment that everything changed. This will become the foundation of GPT-2 and GPT-3 models and everything that followed. So this is the first problem arised in 2018 when researchers trying to build deeper models. So I'm wrapping up this video. In next three videos, we will understand more about these three fixes. So if you like this video, if you love the story, then please do like, share and subscribe to my channel. Thanks for watching. And don't forget, if you have any question, please do comment. I will reply you personally.